Okay, so as you know, you haven't started the astronomy unit yet, and that's because we changed exam boards to support you in actually understanding what's on each paper. So you've got the benefit of this year actually knowing what's on this mock for paper one. But as a consequence, with the previous exam board, they had a different topic order. So we've done everything we can to support you in knowing what this is on the mock. Okay, so first part is we've got an orbit, and it's going to say label the following bits. So in short, what do we need to know? Imagine, there's Mr. Rayside. I've got a piece of string. Whoops, definitely not a piece of string down there. A piece of string wrapped around a bucket. And you know that if I had water in that bucket, I could swing it round and round and round and round, and the water's staying there without going on my head. And what have we got? So the basic idea is, well, we have a force inwards. This is the centripetal force. And then we have a centrifugal force. So I'm going to put a P there. Centripetal. Centrifugal is going to push it outwards. And we're going to see that this force here is very similar to how the planet orbits in terms of these forces. So quick look now. It says label the following letters on the arrows at position 2. So here's position 2. I can see the arrows, and I can see I've got a force going inwards. Well, that's got to be gravitational attraction A. Tick. Done. The next one is instantaneous velocity. Well, this is the planet. Wants to just move in a straight line. That's B. That's its instantaneous velocity. The next part now is, well, we know that we've got a centrifugal force that way and a centripetal force this way. So A and C are the same forces. Centripetal inwards, centrifugal, and I'll write that word there, centrifugal that way. So the next part is, well, we've now got these arrows, and we've drawn vector diagrams before. So we've got an arrow that way, and then that's this one. We've got an arrow here, and you can see, what does this do? We end up with a resultant vector. Well, that's so rubbish, Rayside. Let's change colour. We end up with a resultant force, this vector product, going this way, which means that the planet is constantly going there, 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 and that's what keeps us in orbit. So the orbital velocity is D. Okay, next part. So changing my colour back to some nice sort of blue. It says explain why light from distant stars is redshifted. What do the redshift values tell us about the universe's expansion after the Big Bang? Right, the crucial part now is we're going to have to explain what redshift is, and then link it to the evidence in terms of the Big Bang and what's going on. With the Big Bang being the idea, there was a small explosion, and then everything expanded from that point. So, explain why light from distant stars is redshifted. So what does this mean? Well, it increases in wavelength. Okay, it gets more red. So light emitted from stars is more red. Why? Because as the universe expands, so as the universe expands, the light is stretched, because space is stretched. So you can imagine I'm in a star now, and I emit light of that frequency. What's going to happen now? So some nice blue light. Over time, let's pick a nice red, that one. Over time, space is, so this light's, I don't know, heading off billions of years ago and heading towards us on an insignificant dot over there. And what's going to happen as space stretches, it's going to stretch out this wave so that we increase the wavelength. It becomes more red. So you can imagine an eye on Earth now is going to see this as being redder. Actually, how we see this is we measure spectral lines, and we can see that they just move redder. Okay, so there's the basic idea. So talk about, well, the redshifted is we increase the wavelength of light because space stretches it as it heads towards us. The next part is, what do the values tell us? Apart from a very, very few objects, if here's the Earth, when we look out, pretty much everything is redshifted. All right, so lots, much, I don't even know what to say. Most. Let's go with most. So most stars, most galaxies are red shifted. Now the next part is, if we were to then look at that, if this is distance here and this is your how much you're red shifted, what we can see is the further away you are, the more you're red shifted. All right, so I'm just going to get rid of all of this stuff here. That's really important. So most stars and galaxies are red shifted, but more importantly, if we increase the distance you are away from us, we increase the red shift. Why? Because the stars are moving faster and away from us. Isn't that amazing? So as we increase the distance, we increase the redshift. Why? The stars are moving faster away from us. And not only that, the ones furthest away are moving even faster. So the universe is expanding at an increasing rate. And this is why we've had to come up with dark energy, because we've got absolutely no idea why. But there's your basics. So going back to the question, light from distant stars is redshifted. So redshift, and I'm going to put just the basics now. The wavelength of the light emitted is increased because space is stretching the light. The next part is, what does it tell us? Everything's moving away from us pretty much because most stars and galaxies are redshifted. And the next part is, and not only that, it's expanding at an increasing rate because the stars furthest away from us are the most redshifted because they're moving even faster away from us. So it looks like our universe is accelerating outwards at an increasing rate. Magical. Oh, brilliant. Oh, that bloody